Hello, welcome back to another EncodeVentor tutorial. Today we're going to continue working on the script that I've been working on in the last couple videos. Hopefully we'll get back to it and pretty close to finish it. What we're going to do today is just add in the capability to rotate. So this is a capability that LAMMPS doesn't have very nicely built in. So with this capability you'll be able to rotate continuously. You'll be able to get a continuous rotation. So, as always, you can find these scripts on my GitHub repository, and feel free to look around there. Should be all the scripts from all the videos there. So, with that, we'll just jump right in here. So, first, I've already copied in a function that will help us define a rotation matrix from an axis angle, and I've actually used the Euler-Rodriguez formula for this. So it's just a pretty simple formula. You can find it on Wikipedia, but it's just an easy way to get a matrix form for your rotation matrix from an axis angle. So you'll need something like that, and then next thing we need to do is actually, rotate things. So we'll come down here. So you see we've created our basis right here, but we've never, that's all we've done to it. So what we actually need to do is rotate that basis with our rotation matrix. So let's pick an axis. Let's say, for now, let's just rotate around the x-axis. And we'll rotate at, how about 30 degrees? So then our rotation matrix is, just call the function with the axis and the angle. Now when we rotate our basis, the rotated basis, which we'll just store in the basis again, is just going to be the matrix multiplication of the rotation matrix and the basis. I think this is actually transposed, and that should get you the rotated basis. But we also need to rotate the atom positions. So each of these are vectors. So when we rotate the whole basis, we're going to have to rotate each of these positions as well. So how we're going to do that is we're going to use a list comprehension, and then we'll do a matrix multiplication on each one with the rotation matrix and the atom. We'll do that for each atom in our base atoms. And notice I'm converting it back to a numpy array. So that should get us the rotated basis and the rotated base atoms, so that we have the total basis with the atoms. Alright, so the next thing we need to do is change how we're defining the system. And this is actually going to take a little work, and it took me a little bit to figure out how to do this. But if we just run it like this, I'll run it real quick and you can see what happens. So over here in Python, I'm going to say execute the file, crystalline with rotation. And if we've done it correctly, should work. Yeah. Alright, so now let's open up Oviedo and take a look at what we've made. Now I'm still saving this in crystalline data, so that's going to be there. Here we go. So notice we have indeed rotated it 30 degrees around the x-axis, so that's good. But we've also not filled up our box anymore. So now our system cells are this white box here, and we are not filling it up at all. So we need to find a way to make sure that we still fill up that system box And so that's going to require us redefining how we do this. And here's what we're going to do. So first I'm going to change this to a floating point number, and this is going to be the actual size now. So instead of lattice units, this is actually angstroms. And so we'll do that. And then we'll say, instead of doing that, we're going to also, we're going to define a basis for the system essentially too. Of course, it's just a cube, so it's just a, you know, identity matrix, and then we'll multiply it by the system size. And so that's essentially our system basis. Okay. But now we need to make sure that we get to, so we're going to be iterating over our basis. So remember before we were doing this IJK thing, and it was going from 0, 1, 2, 3, etc. for each of them. So we're going to do the same thing, but we need to make sure that these, the range that we cover for each of those basis components gets us in the system all the way around, like it reaches to each corner. And so that's actually what we're going to do. We're going to get the corners of this system and then figure out what the position is in terms of our basis. So you'll see what I mean as we go here. To get the corners, we're actually gonna use a shortcut. You could just code them in, but what we're gonna do is import from this module called itertools. From itertools, we're going to import product. Now, what this is going to do is, let's see, we'll say corners, and we're going to, we'll do this first, and I'll show you what this does. So if we use product on 0 to system size, and we're going to repeat that 3 times because we're in 3 dimensions. So I'm just going to copy that into here. Oops. I have to import it here as well. All right. So if I do that, you can see that I get these points that are really equal to each of the corners of our cell. So I have the 0, 0, 0, 0, 0, 20, etc. I have 8 points here, so that's each 8 corners of our system. Now, the last thing I'm going to do here is convert that to a numpy array, just so that it plays nice with everything else we have going. Okay, so that's the first thing. Now we actually need to get essentially the vectors to each of these points in terms of the basis. So what that means is we're going to do, essentially how you do that is you do the matrix multiplication of the inverse basis, the inverted basis matrix, with the corner. So I'm going to actually pre-calculate the inverse basis, just because we don't want to invert it every single time. Even though with this basis, it's, you know, we're doing a diagonal matrix, so the invert operation is trivial, but still, it's the principle of the thing. Okay, so now we're going to call it extents, and then we're going to do another list comprehension. And so for each of the corners, we need to do a matrix multiply between the inverted basis and the corner, and that is for each corner in the corners. And we're also going to make that a numpy array. Okay, so now that'll give us the let me show you what that gives us. Oh, well, that's fine. That's giving us an error down here, but it finished what I wanted it to finish. So you can see this is that extents vector, or the extents matrix that we just created. So it gives us the basis vectors essentially to each of the corners. So we're going to be iterating through like an integers, so we're not going to go to, you know, negative 2.4, we're going to go to negative 3. So that means what we need to do for the minimums is find the we need to find the floor essentially. So the floor, and then convert it to an int. So floor will make sure that this is negative 3, and then int will make sure that it plays nice when we put it inside our range function. Okay, so here's what that looks like. We're going to convert it to int for n in the floor and the min of extents and axis 0. I'll explain this in just a second. Alright, so the first thing we're doing is finding the minimum of extents along axis 0. So that finds the minimum along each of these columns. Then we're going to find the floor, then we're going to, you know, make sure we floor each of those. So if I did that here, make sure I have this in, and if I do the floor of the min of extents on axis 0, oops, there we go. You can see we get just 3 numbers. We have 0 because that's the lowest one in this column, negative 3 because that's the floored lowest value in this column, and 0 here. So then this part is just going to convert it to an integer. There's one other thing that I want to do just for safety. So we never want to start lower than or higher than 0. But depending on what our rotation looks like, it might. So I'm going to also throw in here a min between m and 0. And this will just make sure that we always go at least as low as 0, if not lower. Alright, so that's the minimum. The maximums is actually going to be basically identical, except for instead of min, obviously, we're doing max. And we'll say a max of 0 too. So if all of it is giving us negative numbers, we still want to go at least up to 0. So then for a maximum, instead of floor, we'll want to use ceiling so that we get at least as high. And then one other thing I want to do here is I'm actually going to add 1 to here, because when we do our range function in Python, if you do a range between, you know, say negative 2 and 3, you won't get 3 because it doesn't include the end value. So I do want whatever end value is here, so I'm going to add 1 so that it gets up to there. Alright, so I think we're getting really close now. Now what we need to do is modify our generating atoms side here. So instead of ranging over the system size, which as you see from the error doesn't even work anymore, we need to range over the mins on that axis to the maxes. And we're going to do that for all of them with their respective mins and maxes. So 1, 1, 2, 2. Alright. So that part's the same. The Cartesian part should be the same. And oh, one more thing now we need to do. So now if we just run it like this, we can do this and see what it looks like. If we do that, go back into Oviedo and load that again. Oh, well, we have some other changes, but hold on. Okay, so one thing I forgot to do, we need to change our actual writing function here too. While I'm at it, I'm gonna change the name, call it rotated crystalline. So now here, our system size is already in angstroms, so we don't need to multiply it by the lattice parameter. So we can just take that out. Now it should work how we want it to. Now we reload that. Oh, I changed the name. There we go. Looks like we are not quite covering all of our system. Let's go see why that is. So if we look at our mins and our maxes, looks pretty good. I might have forgotten transpose somewhere. There we go. Just missed a transpose. So now, as you can see, it covers our whole system, but that's also not what we want. We want just to fill the system and not, overpower it like that. So every time we create an atom now, we need to check and make sure it's actually in the system. So there's lots of ways we can do that, but what we need to do here is we'll say our atom position is this, and then we'll say that, but we need to check if the atom position is inside the system. So let's say, so one way we can do this is actually convert the atom position into the system basis. So that would be essentially what we did here, except for using the system basis that we defined. So we can do the mat multiply with, and we should pre-compute this as well. That would be a good idea. So we'll invert that one, and then here we'll say an inverse system transpose. As we saw, it does not work. And then we'll do the atom position. Now, so this is going to be in terms of the system. So let me show you what that looks like. I need to define that. And then let's do matrix multiply. Let's pick an atom that's right in the middle of our system. So you can see right in the middle is half, 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 which makes sense because it's right in the middle. But if we picked something outside the system, then the value is greater than 1. So basically what we need to check is that all these are greater than 0 and less than 1. So I'm actually going to put that here, and then I'll make sure that all system position is greater than 0. Make sure that works. Right. So they all need to be greater than 0, and they all need to be less than 1. And actually, we need to, should be less than or equal to 0. We need to include one of the boundaries. So I think that should work. Let's give it a try here. Boom. And now we just have atoms inside our system. Now hopefully this also works for any rotation. Rotating around the x-axis is pretty easy. If we rotate it around a more complicated axis and run that, there you go. And you can see we still have a good crystal structure, just rotated strangely. Alright, so with that you now have the capability to create any crystal rotated in any direction, at least inside of a square. You can actually define similar things like this if you have a more complicated geometry. And then with that you can make any geometry you want. For example, one thing that I've been working on and I'll probably show in a future video, not the next one, but a future one, is doing a Voronoi tessellation of a space and then filling each of those tessellation regions with atoms. So I did something almost identical to this, except for instead of corners, I had my Voronoi vertices. So something very much like that you can do as well. So with that, thanks for watching. I hope this has been helpful. Leave any comments, questions below, and hope to see you next time. Thanks.